You know, there's something deeply unsettling about the question, what happened before the Big Bang? And I don't mean unsettling in a trivial way. I mean it cuts right to the heart of how we understand reality itself. Because here's the thing. We're used to asking what came before about everything. What came before you were born? Well, your parents met, they fell in love, you know the story. What came before the United States? The colonial period, the indigenous peoples, going back and back. We can keep asking that question, and it always makes sense. But when it comes to the Big Bang, when we ask what came before, we might be asking a question that's a bit like asking what's north of the North Pole. And I know how that sounds. It sounds like I'm trying to wriggle out of answering a perfectly reasonable question. But stick with me here, because what I'm about to show you is that the universe is far stranger, far more wonderful than our everyday intuition would ever lead us to believe. Let me start with what we know for certain. The Big Bang, and I want to be very clear about this, the Big Bang explains the evolution of the universe from an initial state of incredibly high density and temperature. We're talking about conditions that are currently way beyond humanity's ability to reproduce in any laboratory. I mean, we've got the Large Hadron Collider, which is pretty impressive, smashing protons together at energies that reach into the trillions of electron volts. But the energies at the very beginning of the universe, we're talking about scales that dwarf even that remarkable machine. So right off the bat, we need to acknowledge something. The most extreme conditions, those first moments of the universe, they're speculative territory. Any explanation of what caused the Big Bang or what might have come before it, we have to take it with a healthy dose of caution. But, and this is crucial, that shouldn't stop us from asking the question. That shouldn't stop us from pushing our understanding as far as it can possibly go. Now, I want you to imagine something with me. Think about time itself. Not the time on your watch, not the time you check on your phone. I mean time as a fundamental feature of reality. We're so accustomed to thinking about time as this river that flows, right? It flows from the past through the present and into the future. And we can trace that river backwards. We can go back to yesterday, last week, last year, 1,000 years ago, 1,000,000 years ago. The question is, can we always keep going back? Is there always a before? Here's where it gets interesting. The phrase before the Big Bang, we know how to parse that sentence. We know what it means to talk about before something. I mean, if I say, before I had breakfast this morning, you know exactly what I mean. If I say, before the Civil War, again, perfectly clear. We understand completely the meaning of that kind of sentence. But here's the thing, and this is what I really want you to wrap your mind around. It could be that when it comes to the Big Bang, that sentence actually doesn't mean anything. Let me give you an analogy that I think Stephen Hawking used beautifully. Imagine you're walking on the surface of the Earth, and you're walking north. You're in, say, Texas, and someone asks you, hey, which way is north? And you point in that direction, and you keep walking. You get to Oklahoma, someone asks you the same question, you point north, you keep walking, you get to Kansas, Nebraska, the Dakotas, you're heading into Canada, and all along the way, the question, which way is north, makes perfect sense. But now imagine you keep going, and you reach the North Pole. You're standing right there at 90 degrees north latitude, and someone comes up to you and says, hey, which way is north? And you look at them, and you realize that question doesn't have an answer, not because you don't know the answer, but because the question itself doesn't make sense anymore. There is no north of the North Pole. That's where north begins. You can't go more north than the North Pole. Now, here's the remarkable thing. It might be that the Big Bang is the temporal equivalent of the North Pole. It might be the place where time itself began. If you go back 1 billion years, okay, there's stuff happening. The universe is younger. 10 billion years, universe is even younger. But if you go back 13.8 billion years, that's where we hit the Big Bang. It might be that's where time starts. And you can't go more back in time than the very origin of time itself. Now, I can see you thinking, wait a minute, that can't be right. Time had to start sometime, so what was there before time started? And that's exactly the trap our intuition leads us into. Because the phrase "before time started" contains its own contradiction. If time hadn't started yet, there's no before. Before is a temporal concept. It requires time to already be in place. Let me put it another way. The question, what happened before the Big Bang, might be a bit like asking, what does the color blue smell like? The question has the grammatical structure of a meaningful question: subject, verb, object, everything in the right place. But it's mixing categories that don't mix. Colors don't have smells. And if time began at the Big Bang, there might not be a before for anything to happen in. But now, and this is where it gets really fascinating, I'm not saying that's definitely the answer, I'm saying that's one possible answer. Because here's what you need to understand. We don't know. We don't know with certainty. And that's actually one of the beautiful things about science. We're honest about the boundaries of our knowledge. The Big Bang Theory, which is based on Einstein's equations of general relativity, it tells us something profound about the universe. It tells us that if we trace the universe backwards in time, everything gets denser, hotter, more compressed, and the equations say that if you go back far enough, you reach what's called a singularity, a point where density and temperature become infinite, where the equations themselves break down. Now, when a physicist tells you the equations break down, what we mean is the equations are giving us nonsensical answers. They're telling us that certain quantities become infinite. And we know that's not physically reasonable. It's the equation's way of saying, hey, I don't apply here anymore. You need a better theory. And that's exactly the situation we're in. General relativity, Einstein's beautiful theory of gravity and space-time, it works fantastically well for describing the large-scale structure of the universe. I mean, it predicted the existence of black holes. It predicted gravitational waves, which we detected just a few years ago in 2015, more than a century after Einstein wrote down the equations. It's an astonishingly successful theory. But general relativity doesn't include quantum mechanics. And quantum mechanics is the physics of the very small, the physics that governs atoms and particles and the fundamental constituents of matter. And here's the problem. The early universe wasn't just hot and dense, it was hot and dense enough that quantum effects should have been important. You can't ignore the quantum world when everything in the universe is compressed to subatomic scales. So what we really need, if we want to talk sensibly about the very first moments of the universe, is a theory of quantum gravity, a theory that combines Einstein's general relativity with the principles of quantum mechanics. And here's where I have to be honest with you. We don't have that theory yet. Not completely. We have candidates. String theory is one that I've spent much of my career working on, but we don't have a final, complete, experimentally verified theory of quantum gravity. And that means that when we talk about times earlier than what's called the Planck time, that's about 10 to the minus 43 seconds, an almost incomprehensibly short moment, we're really in speculative territory. The Planck time is the earliest period in the history of the universe where we can confidently apply the physics we currently understand. Before that, the theories we have now, they might not apply. Now, you might be thinking, okay, so we can't say for sure what happened before the Big Bang, or if there even was a before. But surely physicists have some ideas. And yes, absolutely, we have ideas. We have several ideas, actually, and they're all fascinating. And they each tell a different story about what reality might be like. But before I get into those ideas, and I promise you we're going to explore them in detail, I want to make sure you understand why this question matters. Why should you care about what happened before the Big Bang, or whether the question even makes sense? Here's why. This question is really about understanding the nature of time itself. Time is something we all experience every moment of every day. It's the most familiar thing in the world. And yet, it's also one of the most mysterious. Does time flow like a river, or is that just an illusion? Does time have a beginning, or has it always existed? These aren't just abstract philosophical questions, they're questions about the fundamental structure of reality. And here's something I find deeply moving. We're living in an era where for the first time in human history, we actually have the mathematical and observational tools to make progress on these questions. We can't answer them definitively yet, but we can frame them precisely. We can test different ideas against what we observe, and we can start to narrow down the possibilities. Let me tell you what we do know with pretty high confidence. We know that about 13.8 billion years ago, the universe was in a state of incredibly high density and temperature. We know this because we can observe what's called the cosmic microwave background radiation. It's basically the afterglow of the Big Bang, light that's been traveling through space for more than 13 billion years, and we can detect it with our instruments. It's really quite remarkable. You can actually tune an old television set between channels, and about 1% of that static, you see, that's ancient light from the beginning of the universe. You're literally seeing the Big Bang on your TV screen. We also know that the universe has been expanding ever since that hot, dense, early state. And we can measure that expansion. We can see distant galaxies moving away from us, and the farther away they are, the faster they're moving. This was discovered by Edwin Hubble in the 1920 seconds, and it was one of the most important discoveries in the history of cosmology, because it told us the universe isn't static, it's changing, evolving over time. Now, if the universe is expanding and we run the clock backwards, everything gets closer together. The galaxies that are now millions and billions of light years apart, they were once much closer, and if you keep going back, they were all in the same place. Space itself was compressed, and that's what the Big Bang represents. Not an explosion in space, but an expansion of space itself. But here's where our intuition can lead us astray. When you hear Big Bang, you might picture something like fireworks, a point in space where an explosion happens and matter goes flying outward into empty space. But that's not quite right. The Big Bang wasn't an explosion in space, it was an expansion of space. Space itself was compressed to an incredibly small size, and it's been stretching and growing ever since. And this is why visualizing the Big Bang by comparing its size to everyday objects can be misleading. When physicists talk about the size of the universe at the Big Bang, we're talking about the size of the observable universe, the part of the universe we can potentially see, not necessarily the whole universe. The whole universe might be much, much larger. It might even be infinite. We don't know. Let me pause here and make sure this point is clear, because it's important. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's a sphere centered on us with a radius of about 46 billion light years. Now, you might think, wait, if the universe is only 13.8 billion years old, how can the observable universe be 46 billion light years across? Good question. The answer is that space itself has been expanding. So light that was emitted close to us has been stretched as space expanded, and the objects that emitted that light have been carried away from us by the expansion of space. But beyond the observable universe, there might be more universe. Maybe a lot more. Maybe infinitely more. We can't see it, because light from those distant regions hasn't had time to reach us yet. But it might be there. So when we talk about the Big Bang, we're really talking about the beginning of the observable universe. And that's an important distinction, because it opens up some fascinating possibilities for what might lie beyond what we can see. Now, let me take you through what we know happened in the early universe, because it's an astonishing story. I want to give you a sense of the timeline, the sequence of events that unfolded as the universe expanded and cooled from that initial hot, dense state, the very first moment, the first picosecond, that's 1/1,000,000th of a second, includes what we call the Planck epoch. This is when the laws of physics, as we currently understand them, might not apply. The universe is so hot and so dense that quantum effects dominate. And we'd need that theory of quantum gravity to really understand what's happening. Then comes inflation. This is a really crucial idea that we're going to explore more deeply later. The basic idea is that the universe underwent a period of incredibly rapid expansion, faster than the speed of light. Now, that might sound like it violates Einstein's relativity, which says nothing can move faster than light, but it doesn't, because it's not matter moving through space, it's space itself expanding. And there's no speed limit on that. This inflationary period lasted an incredibly short time, maybe 10 to the minus 32 seconds. But in that time, the universe expanded by an enormous factor, maybe 10 to the 26 or more. That's like taking something the size of an atom and inflating it to the size of a galaxy, all in a tiny fraction of a second. It's almost incomprehensible. Why do we think inflation happened? Well, it solves several puzzles about the universe. It explains why the universe looks pretty much the same in all directions. We call that homogeneity. It explains why the geometry of space is so flat. And it explains where the tiny ripples in the density of the universe came from, ripples that eventually grew into galaxies and clusters of galaxies. After inflation, the universe is still incredibly hot. We're talking about temperatures of maybe 10 to the 27 degrees. That's a billion degrees. At these temperatures, the fundamental forces of nature are unified. Gravity has separated out, but the electromagnetic force and the strong and weak nuclear forces are still part of a single unified force. As the universe continues to expand and cool, these forces separate from each other. First, the strong nuclear force splits off, then the weak and electromagnetic forces separate. This is called symmetry breaking, and it's one of the most beautiful ideas in modern physics, the idea that the fundamental forces we see today all came from a single unified force in the early universe. By the time we get to about 1 second after the Big Bang, now we're in territory where we can be pretty confident about the physics. The universe is cooled to about 10 billion degrees. It's filled with a sea of particles, neutrons, protons, electrons, they're antiparticles, positrons, photons, and neutrinos. It's this incredibly dense particle soup, and something important happens around this time. The neutrinos decouple. What that means is they stop interacting with other particles. They just stream freely through the universe. And those neutrinos, in principle, they're still around today. They form what we call the cosmic neutrino background. We haven't detected it yet. Neutrinos are notoriously hard to detect because they barely interact with anything, but it should be out there filling all of space. By about 2 minutes, so we're 2 minutes after the Big Bang, now conditions are right for nuclear fusion. Protons and neutrons start sticking together to form the nuclei of heavier elements. About 25% of the protons and all the neutrons fuse into helium nuclei with small amounts of deuterium and lithium. This is called Big Bang nucleosynthesis, and it's one of the great triumphs of the Big Bang theory because we can calculate how much of each element should have been produced, and those calculations match beautifully with what we observe in the universe. At 20 minutes, the universe has cooled enough that nuclear fusion stops, but it's still too hot for neutral atoms to exist. The electrons are still zipping around freely, not bound to any nuclei. And because of this, photons, particles of light, can't travel very far without bumping into an electron. The universe is opaque at this point, kind of like trying to see through fog. This state continues for a while, quite a while by human standards, though not so long on cosmic scales. For about 380,000 years, the universe is this hot, opaque plasma, but it's cooling all the time as it expands. And then, about 380,000 years after the Big Bang, something remarkable happens. The universe is cooled enough to about 3,000 degrees that electrons can finally attach to nuclei and form neutral atoms, mostly hydrogen and helium with traces of lithium. This is called recombination, though that's a bit of a misnomer because these electrons and nuclei were never combined before. And when recombination happens, suddenly the universe becomes transparent. Those photons that had been constantly scattering off free electrons, now they can travel freely through space. And those photons are still around today. They've been stretched by the expansion of the universe, so instead of being visible light, they're now microwaves. That's the cosmic microwave background I mentioned earlier. It's the oldest light in the universe, the most ancient thing we can observe. When astronomers first detected the cosmic microwave background in 1965, it was completely by accident. Two scientists, Arno Penzias and Robert Wilson, were working with a large radio antenna, and they kept detecting this annoying background noise that they couldn't get rid of. They thought maybe it was bird droppings on the antenna. That's how mundane the discovery seemed at first, but it turned out to be the echo of the Big Bang itself. They won the Nobel Prize for it. Now, the universe after recombination, it's mostly just hydrogen and helium gas spread pretty uniformly through space. But pretty uniformly is the key phrase. There are tiny variations in density, tiny ripples left over from the inflationary period. And those ripples, they're crucial because gravity amplifies them. Regions that are slightly denser have slightly more gravity, so they pull in more matter, which makes them even denser, which increases their gravity even more. It's a runaway process. Over millions of years, those tiny ripples grow into large structures, first stars, then galaxies, then clusters of galaxies, and eventually the cosmic web we see today with vast filaments of galaxies separated by enormous voids. The first stars form maybe 100 to 200 million years after the Big Bang. These aren't like the sundae. They're massive, maybe 100 or even 1,000 times the mass of the sun, and they're made of nothing but hydrogen and helium. No carbon, no oxygen, no iron. Those elements don't exist yet. They'll be created inside these stars, and when the stars explode as supernovae, they'll scatter those elements through space, seeding the next generation of stars. And this is where we come in a sense, because every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, all of that was created inside a star. We're made of stardust, as Carl Sagan liked to say, and it's literally true. So that's the story of the universe as we understand it, from the Big Bang to today. It's a story we've pieced together from observations and mathematics, from theory and experiment, and it hangs together beautifully. The different pieces of evidence, the expansion of the universe, the cosmic microwave background, the abundances of light elements, the formation of structure, they all fit together into one coherent picture. But here's the thing. It's a story that starts at the Big Bang. It tells us what happened after. It doesn't tell us what caused the Big Bang. It doesn't tell us what came before, or if there even was a before. Now, you might be thinking, well, okay, maybe we can't know what happened before the Big Bang. Maybe it's just beyond the reach of science. And you know what? Maybe it is. That's a legitimate possibility. There might be questions that science, by its very nature, cannot answer. But I don't think we should give up so easily. I think we should push as far as we can, use every tool at our disposal, mathematics, observation, experiments, even thought experiments, and see how far we can get. Because here's the thing. People have said before that certain questions were beyond the reach of science, and they were wrong. People said we could never know what stars are made of, and then we invented spectroscopy, and we figured it out. People said we could never see atoms, and then we invented electron microscopes. People said we could never detect gravitational waves, and then we built LIGO, and we detected them. So maybe, just maybe, we can make progress on this question too. Maybe we can develop a theory of quantum gravity that tells us what happens at the Planck time and earlier. Maybe we can find observational signatures, something we can measure or detect that tells us about the pre-Big Bang era, if there was one. And physicists have proposed ideas. Oh, have we proposed ideas? Some of them are quite conventional in the sense that they use well-established physics in creative ways. Others are, shall we say, more speculative. They require new physics, new principles, whole new ways of thinking about reality. Let me give you a taste of what's out there, what physicists have been thinking about. And I want to emphasize these are ideas, not established facts. They're possibilities we're exploring, trying to figure out which ones might be true and which ones we can rule out. One idea goes back to something I mentioned earlier, inflation. Remember, that's this period of incredibly rapid expansion in the very early universe. Now, here's the interesting thing. The same physics that produces inflation in one region of space can produce it in other regions too. And if inflation happens in one place, there's no reason to think it only happens once. So you could have a situation where space is undergoing inflation in many different regions, at many different times, and in any given region, inflation eventually ends, it stops, and when it ends, you get a hot, dense, expanding universe. You get a Big Bang. But this is just one Big Bang among many. It's like bubbles forming in boiling water. Each bubble is its own little universe expanding and evolving according to the laws of physics. This is sometimes called eternal inflation, and it leads to the idea of a multiverse. Many universes, maybe infinitely many, all existing within this larger inflating space. And our Big Bang, it's just one of these bubbles. It's the event that created our observable universe, but it's not the only one. There are others, maybe infinitely many others, beyond our horizon. Now, if that's true, and I'm not saying it is, I'm saying it's a possibility, then the question, what came before the Big Bang, has a very concrete answer. What came before was this larger inflating space, and what caused the Big Bang was the end of inflation in our particular region. The Big Bang wasn't the beginning of everything, it was just the beginning of our little corner of reality. And here's something really wild. In this scenario, different bubble universes might have different laws of physics. The fundamental constants of nature, things like the strength of gravity or the mass of the electron, those might be different in other bubbles. The laws themselves might be different. Why? Well, it has to do with something called symmetry breaking that I mentioned earlier. When the universe cools from very high energies, certain symmetries get broken, and which way they break can be random. It's kind of like a pencil balanced on its tip. When it falls, it has to fall in some direction, but which direction is random. In different bubble universes, the symmetries might break in different ways, leading to different effective laws of physics. This raises all sorts of fascinating questions. Are we just lucky that our universe has laws that allow for stars, planets, and life? Or is there some deeper reason? It's a question that keeps physicists up at night. I know it keeps me up sometimes. But let me tell you about another idea, a very different one. It comes from thinking about quantum mechanics in a cosmological setting. In quantum mechanics, we have this notion that particles can be in what's called a superposition. They can be in multiple states at once until you measure them. The classic example is Schrödinger's cat, which is supposedly in a superposition of being both alive and dead until you open the box and look. Now, what if you apply that same quantum logic to the universe as a whole? What if the universe itself can be in a superposition? And in particular, what if there's a quantum state that describes the universe simply popping into existence without any prior cause? This is the idea behind models like the Hartle-Hawking no-boundary proposal. The idea, roughly speaking, is that if you go back to the very beginning and include quantum effects, time itself becomes sort of fuzzy and space-like. The distinction between time and space breaks down, and in this picture, there's no sharp moment of beginning. There's no singularity. The universe just is. It's self-contained, with no boundary in time, hence no boundary. Stephen Hawking liked to illustrate this with the question, what's south of the South Pole? The answer is nothing. Not because there's a wall or a boundary there, but because the question doesn't make sense in terms of the geometry of the Earth. Similarly, in the no boundary proposal, asking what came before the Big Bang doesn't make sense because there is no before time itself is bounded, but in a smooth way with no edge or beginning. It's a beautiful idea, mathematically elegant. Whether it's right, we don't know yet. It's hard to test because it makes predictions about the very earliest moments of the universe, and observing those directly is incredibly challenging. Then there's string theory, my own field of research. String theory suggests that the fundamental constituents of nature aren't point particles, but tiny, vibrating strings of energy. And when you work out the mathematics of string theory, something fascinating emerges. The theory requires extra dimensions of space beyond the three we experience every day. Now, these extra dimensions are thought to be curled up, compactified, so small that we don't notice them. But their geometry, the precise way they're curled up, affects the physics we observe. Different shapes for the extra dimensions give you different particle physics, different forces, different constants of nature. And here's where it connects to cosmology. In something called the brain world scenario, our entire observable universe might be confined to a three-dimensional brain. Think of it like a membrane embedded in a higher dimensional space. The Big Bang in this picture might have been caused by a collision between brains. Two brains smack into each other, and the energy of that collision creates the hot, dense state we call the Big Bang. There's even a cyclic version of this idea where the brains collide periodically, over and over. Each collision creates a Big Bang, the universe expands and evolves, eventually things slow down and reverse, the brains come back together, a big crunch, and then they collide again. Big bang, big crunch, big bang, big crunch, over and over through eternity. In this scenario, not only is there something before our Big Bang, there was a previous cycle, a previous universe that contracted and then bounced back out. Time extends infinitely into the past and infinitely into the future with these cycles of expansion and contraction. Does that sound crazy? Yeah, it probably does. And I want to be honest with you. These ideas are highly speculative. They're not established science in the way that, say, the expansion of the universe or the existence of the cosmic microwave background are established. But they're not just wild speculation either. They're based on serious mathematics, extensions of theories that have been very successful in other domains. The question is whether any of these ideas can be tested. Can we find observational evidence that would support one of them and rule out others? That's the challenge. That's what physicists are working on right now. And here's something you should know. The fact that we're even able to ask these questions, to think about them rigorously using mathematics, and to propose ways of testing them, that's a fairly recent development in human history. 100 years ago, cosmology was barely even a scientific field. We didn't know that other galaxies existed. We didn't know the universe was expanding. We certainly didn't have the mathematical tools to think about quantum gravity or extra dimensions or multiverses. Now we do. We have the tools, we have the observations, and we have the creativity to push these ideas as far as they'll go. And who knows, maybe in our lifetimes, maybe in the next generation, we'll make a breakthrough. Maybe we'll find a signature in the cosmic microwave background, or in the distribution of galaxies, or in some phenomenon we haven't even thought to look for yet that tells us what really happened at the very beginning. Or maybe we'll never know. Maybe this is one of those questions that's permanently beyond our reach. But I'll tell you what, I'd rather live in a universe where we don't know, where there's still mystery, where there are still frontiers to explore, than in a universe where everything is settled and there's nothing left to discover. Because here's what really matters: the question itself, the fact that we can ask it, that we can think about it, that we're driven by this deep curiosity about where we came from and what it all means. That's what makes us human. That's what makes us special in this vast cosmos. So when someone asks me, what happened before the Big Bang? And people ask me this all the time. I don't say, that question doesn't make sense. I say, that's one of the deepest questions we can ask. And we're working on it. We don't have the answer yet, but we're not giving up. Because science isn't just about the answers we've found, it's about the questions we're still asking. And this is one of the biggest questions there is. Now, you might be wondering, even if we can't say for certain what happened before the Big Bang, can we at least say something about why the Big Bang happened? What caused it? What triggered this incredible expansion that created everything we see? And here's where I want to introduce you to an idea that I find absolutely fascinating. It has to do with gravity, good old gravity, the force that keeps our feet on the ground and the moon in orbit around Earth. We're all familiar with gravity as an attractive force, right? Drop something, it falls down toward the Earth. The Earth orbits the sun because of the sun's gravitational attraction. Gravity pulls things together. But, and this is where Einstein comes in, again, gravity can also be repulsive. Now, I know what you're thinking, wait, repulsive gravity, that doesn't make any sense. Everything falls down, not up. And you're right, in our everyday experience, gravity is always attractive. The gravity created by the Earth, by the sun, by any ordinary object, it always pulls things together. But Einstein's equations, those same equations of general relativity that describe the large-scale structure of the universe, they actually allow for gravity to push as well as pull. And the key is what kind of stuff you're talking about. If you have a compact object, like a rock or a planet or a star, something with matter that's localized in space, that creates attractive gravity. But if you have energy that's spread uniformly through a region of space, that creates repulsive gravity. It pushes things apart instead of pulling them together. Why? Well, it has to do with the properties of whatever is filling that space. In Einstein's equations, both energy density and pressure contribute to gravity. For ordinary matter, the pressure is negligible compared to the energy density, so you get attractive gravity. But for certain kinds of fields, and this is where it gets technical, the pressure can actually be negative. And when you have negative pressure, you get repulsive gravity. Now, what does this have to do with the Big Bang? Well, here's the idea. If the very early universe was filled with a uniform bath of this special kind of energy, physicists call it an inflaton field, though the name doesn't really matter if it was filled with that, then it would be subject to repulsive gravity. And repulsive gravity doesn't gently push things apart, it pushes things apart explosively. It causes space itself to expand at an incredible rate. And this, many physicists believe, is what powered inflation. It's what caused that period of incredibly rapid expansion in the first tiny fraction of a second after the Big Bang. In fact, you could even say that the burst of the Big Bang itself, the thing that got the expansion started, was triggered by this repulsive gravity operating in a small region of space. It's like a spark that ignited the explosive growth of the universe. And here's something really remarkable. We actually have evidence that something like this is happening even today, right now, in the present universe. Because when we look at distant galaxies, we see that they're not just moving away from us, they're accelerating. The expansion of the universe is speeding up, not slowing down. This was discovered in 1998, and it was such a surprise that the discoverers won the Nobel Prize in 2011, because everyone expected that gravity would be slowing the expansion down, pulling galaxies back toward each other, but instead it's speeding up. And the best explanation we have for this, not the only explanation, But the most widely accepted one is that there's a form of energy filling space, something we call dark energy, and this dark energy creates repulsive gravity. It's pushing the expansion of the universe to accelerate. Now, the dark energy that we think is causing the current acceleration, it's very dilute. It has an energy density of maybe 10 to the minus 9 joules per cubic meter. That's incredibly small. But the inflaton field in the early universe would have had an energy density that's vastly, vastly greater, maybe 10 to the 100 or more times greater. And that enormous energy density created a repulsive gravity so strong that it inflated space by an enormous factor in an incredibly short time. So, in a sense, we've seen gravity be repulsive. We're seeing it right now in the accelerating expansion of the universe. We just need to imagine that same effect, but much, much stronger, operating in the very early universe. And that gives us the Big Bang, but this still leaves us with a question. Where did this inflaton field come from? Why was the early universe filled with it? And here's where we get to the really speculative part, the part where we're pushing beyond what we know for sure and into the realm of ideas and possibilities. One idea is that this inflaton field wasn't created at all. It was just there as a background property of space. And occasionally, randomly, due to quantum fluctuations, a small region of space would find itself with this field at just the right value to trigger inflation. And once inflation starts in that region, boom, you get a Big Bang, you get a new universe. And remember eternal inflation that I mentioned? In that picture, this is happening all the time in different regions of space. Little pockets of space randomly enter the right conditions for inflation, they inflate and become new universe bubbles, and the process goes on forever. Our Big Bang was just one of these random quantum events creating our particular universe bubble. Another idea, and this is where we really need that theory of quantum gravity, is that the universe, or really the multiverse, is eternally in existence, undergoing these quantum fluctuations. Sometimes a fluctuation is just right to create an inflating region, and that becomes a universe like ours. There's no ultimate beginning, no first cause. It's quantum processes all the way back. Now, I know this sounds crazy. I know it does. But you know what? The universe doesn't owe us intuitive answers. The universe doesn't care whether its workings make sense to creatures who evolved to hunt and gather on the plains of Africa. Reality is what it is, not what we'd like it to be. And the remarkable thing, the truly astonishing thing, is that we've developed the mathematical and observational tools to actually investigate these questions. We're not just making up stories. We're using the same methods that allowed us to predict the existence of the Higgs boson, that allowed us to detect gravitational waves, that allowed us to measure the age of the universe to within 1% accuracy. So when I tell you about these wild ideas, multiverses and quantum creation and repulsive gravity, I'm not just spinning fantasies. These are extrapolations, careful extrapolations from theories that have been tested and proven successful in other regimes. Could they be wrong? Absolutely. In fact, most of them probably are wrong, or at least incomplete. That's how science works. You propose ideas, you test them, you refine them, and gradually you narrow in on the truth. Or at least you narrow in on better and better approximations to the truth. But here's what I want you to take away from all this. The question, what happened before the Big Bang, is not off limits. It's not a question that science can't address. It might be a question that we'll never fully answer, but we can make progress on it. We can develop theories, we can look for observational signatures, we can rule out some ideas and refine others. And in the process, we learn more about the nature of time, the structure of space, the origin of the universe. We learn more about reality itself, and that's worth doing, even if we never get a complete answer. Because at the end of the day, what drives us as scientists, what keeps us working late into the night on these problems, isn't just the desire for answers. It's the sense of wonder. It's the feeling you get when you realize how strange and beautiful and intricate the universe is, when you realize that we're part of something so much larger than ourselves, so much more ancient and vast and mysterious. And when we ask, what came before the Big Bang, we're asking about our ultimate origins. We're asking where we came from in the deepest sense possible. That's a question that's driven human beings since we first looked up at the stars and wondered what they were. We're in a unique position now, a privileged position, where for the first time in human history, we have the tools to actually make progress on that question. We might not find the final answer in our lifetimes, but we can push the boundaries of knowledge further than they've ever been pushed before. And that's what we're going to explore in the next part of our journey together. We're going to dive deeper into these ideas: inflation, the multiverse, quantum creation, the nature of time itself. We're going to look at the evidence, we're going to examine the theories, and we're going to try to make sense of this most profound of questions, because if there's one thing I've learned in my career as a physicist, it's this: the universe is always stranger and more wonderful than we imagine. And the more we learn, the more we discover just how much we still have to learn. The mystery deepens even as it becomes clearer. And that, to me, is the most exciting thing of all. So we've established that the question, what happened before the Big Bang, might be one of those questions that sounds simple but opens up into deep, strange territory. And we've talked about how time itself might have begun at the Big Bang, which makes asking about before a bit like asking what's north of the North Pole. But now I want to take you deeper into this, because there's another way to think about the problem, one that doesn't require time to have a beginning, one that suggests our Big Bang might not have been the beginning of everything. Let me start by being really clear about something that often gets muddled in popular discussions. When we talk about the Big Bang, we're not talking about the creation of all of space. We're talking about the evolution of the observable universe from a hot, dense state. And that's a crucial distinction. The observable universe, that's the region of space from which light has had time to reach us. But the whole universe, that might be much, much bigger. It might even be infinite. And here's where it gets interesting. If the universe is infinite now, and it's been expanding, well, you might think, okay, if I run the clock backwards, doesn't an infinite universe get smaller until it's finite? And the answer is no, not necessarily. An infinite universe that's expanding remains infinite as you go backwards in time. It just gets denser. The spacing between things gets smaller, but there's still an infinite amount of stuff. So right away, we can imagine that the Big Bang might have been an interesting event, but not the first event in the totality of reality. It might have been the first event that triggered the expansion of our part of space, but it could be that there's a grander realm of space within which we sit as a small part, and that grander realm might have been there for a much longer period of time. It might have experienced its own Big Bangs, many of them, perhaps. It might be a collection of Big Bangs extending infinitely far into the past. Now, let me give you a way to visualize this, because I think it'll help. Imagine space as this enormous, maybe infinite expanse. And imagine that in different regions of this space, at different times, conditions become just right for inflation to begin. Remember inflation? That's the period of incredibly rapid expansion powered by repulsive gravity. So you've got this region over here where inflation starts, and boom, it creates a rapidly expanding bubble. That bubble is what we would call a universe. Inside that bubble, when inflation ends, you get a Big Bang, a hot, dense state that then expands and cools and forms galaxies and stars and eventually planets and people. That's one universe. But over there, in a different region, another patch of space enters the right conditions, and inflation starts there too. Another universe bubble forms. And over there, another one